Today we are going to talk about derivative 2, means second part of the derivatives. So, first we are going to talk about the rules about computing with derivatives, and then we are going to talk about the famous chain rule which is among them, and then we will show a very useful application of that. Rather we will try to correct one misnomer which usually is done by calculus students, and then we are going to talk about the second derivative and higher derivatives. So, if you have a function f and you have a function g, so by a function f plus g, the added function, if you evaluate it at x, it is nothing but fx plus gx. So, the question is, what is the meaning of the ddx of f plus g at a given point x? You can simply prove even from the first principle, the limit, the definition, that this is nothing but ddx of fx plus ddx of gx or dg dx. You can write whichever way you think it is comfortable to you. Now, what about subtraction? Of course, you can replace plus with minus. The more curious thing is what is the meaning of this. Here again, if you use the definition, I think you should, everyone who has forgotten his high school calculus should make a little trial of this. It is always good to do some exercise by yourself. Then this would be nothing but g of x into ddx of f at x plus f of x plus ddx of g at x. That would be the answer. This is a well known fact, and of course we need to talk about this. Of course, gx here cannot be equal to 0 any time. If this is the case, again the first principle will show that this is what you have. You will have one has to be very careful in this, g of x into the derivative of f minus f of x into the derivative of g. This rule becomes helpful many times. The key rule that I want to mention here is the chain rule. Now, suppose you have a function f, when you write function f compose g evaluated at x. I have already spoken to you about this composition of functions. This can be viewed as f g first computing g of x, g first operated on x, then f is operated on gx. Now, the question is, what is the meaning then of ddx of f compose g of x? So, this is first, now f here first looks like a function whose independent variable is the function g, the value the gx, the function g itself is the independent variable here. So, basically then you have to take the derivative, do it in two steps, take the derivative of f with respect to g. I am writing here x means to say that I am evaluating it at a point x. If you do not want to write the x, that also is fine. So, you can write just ddx of f compose g. So, ddx of g, of course the df dg evaluated at the point gx, right, that is more important, into dg of dx evaluated at the point x. So, you can write this in a more apparent shorthand that we use. Now, I have often seen calculus students do the following mistake. So, they often write dy dx as 1 by dx dy or dx dy as 1 by dy dx. When I have asked some, as per my experience goes, when I have asked certain students, they have simply said that okay, it is so obvious, it should be like that, but it is not so obvious, it is not, you are not inverting fractions, you are not inverting numbers. It has, one has to remember that here these are operators, so you cannot invert them as numbers. So, how do you get this thing? This comes from the chain rule. Now, consider a function y is equal to fx, where f is a bijective function, means it has an inverse. So, which means x can be written as f inverse of y, which would imply that I can write y as f of f inverse of y. That is, so there is one y linked to one x, so I bring the y back to x, and then even if I apply the f, it will take me to y. So, that is exactly what is happening. The function has to be absolutely a bijective map 1 to 1. So, if this happens, now what is f inverse y? It is actually x. So, what is now dy of dy? Now, you know dy of dy is 1. This can be obtained by the first principles, that is just compute through definition, the limit, which is obvious, at least. Before it is very simple, you can just check it out. If I tell you this, then this will be basically letting you, basically it would be like teaching you ABCD. So, now what I need to do is now how do I apply the chain rule in this case. So, this is basically, you can write this as f composed f inverse of y. So, how do I apply the chain rule? So, f is first viewed as a function of f inverse y, but f inverse y is itself x. So, basically this can be viewed as x. So, what you are doing, you are first taking the del f of del f inverse, which is del f of del x, into the chain rule del x. So, this is f inverse again as a function of y. So, f is actually your x, basically is your y. So, I can write instead of del f del x is same as del y del x, because y is equal to f of x. So, this is, so what is wow? So, this product of these two derivatives, these are of course numbers. Dy dx itself is a number, dy is not a number, dx is not a number. So, this product is equal to 1, and then of course you can write that dy dx is 1 by dx dy. One has to remember this is only possible in this situation when y is an invertible function. If y is not invertible function, you cannot write such stories. So, if you can take the derivative of f, if it is differentiable, then you can take the derivative of f once more, first time, second time, third time, and so on. For example, if you have f of x, then you take the first derivative, and suppose you can take the second derivative, if you can take the third derivative, you can do like this. Now, this is of course written as dy dx or del f del x, does not matter whatever you want to write. I am just writing as dy dx. So, this is written as d2y dx2, second order derivative. Third order derivative is written as d2y, y is f actually, dx3, and so on. You can have the nth order derivative dny dxn. You can compute this, but there is some formula called Fadi-Bruno's formula, which we are not going to discuss here. It might be, for example, it might be possible that there is a function which is differentiable at differentiable first, but not differentiable for the second time. For example, So, if I write a function like this, which is x square sin 1 by x when x is not equal to 0 and is equal to 0 when x is equal to 0, then this I would like you to try out at home. This is very important. This function has f dash 0, but no f dash double 0. Check whether what I have told is true. It is very important that those who have access to internet, computers, etc., or MATLAB or Mathematica, they should try to plot. So, this can be considered as one homework for those who have just enrolled in the course, may not take an exam, but they can just try it out for fun. Now, let us look into this whole issue once again. So, you can have a function can have derivatives nth time and all, for example, f x equal to x square, f x is equal to sin x. For example, let us take f x equal to sin x, f dash x is cos x, f double dash x is minus sin x. So, f triple dash x is again minus cos x, and f 4 times x is sin x. So, you see there is a pattern which emerges, and you can actually, I will like you to write down the general formula in this case. So, f x that's a little bit of trial and error with mathematics. So, f x is equal to sin x, f dash x is equal to cos x, f double dash x is equal to minus sin x, f triple dash x is equal to minus cos x, f 4 dash x equal to sin x. Now, once this is done, let us talk about the physical significance of the derivative. The physical significance of the derivative. Now, suppose you have a particle which is moving, maybe in a straight line, does not matter, or maybe at every given time you note its position. So, maybe the particle is actually moving starting from a time t equal to 0, a free particle is moving along a straight line at every time t equal to say 1, t equal to 2, etc. 1 hour, 2 hour, or 2, 1 second, 2 seconds, does not matter. So, at some time t you are noting its position. So, at any time t its position is been given by x of t. So, you can have t and x of t. So, you can start with 0 and it can just go up like this, or it could be some curve, does not matter. Now, what is the meaning of velocity at a given point? That was one of the very important questions that was first faced by Newton while developing mechanics. So, it was Newton who brought in the idea of instantaneous velocity. I can tell you that whenever I think of this term instantaneous velocity, means velocity of a particle, for example, a particle is moving across, a particle is moving, and then this is a particle which is moving, let the pen is moving, and then at any point suddenly at one particular instant you want to know the velocity. Of course, you know velocity is a vector which is has a quantity and a direction. So, it is moving in a certain direction and suddenly you want to know its velocity. For example, a particle is moving along a curve, at every point its velocity is along the tangent to that curve. It is not so obvious and not so intuitive that you are talking about velocity at right at a given instant of time. So, what do you have to measure? That how do you measure velocity? Largely we measure speed. So, a car has travelled a distance from A to B. So, what is the distance between A to B and the time it has taken to go from A to B? We take the ratio of the distance covered by the time and we say that was the basically the average speed of the car. Now, here you are talking about just a small movement away, you are talking about velocity exactly at a point. So, how would you do it? So, Newton first thought of incremental changes. So, let us look at the velocity when the distance profile from t, and from t I had a very small time delta t. So, in little time how much it has moved? Okay. Think of delta t as positive at this moment. You can think of it as negative, means you are looking at it from the backward thing. See, the interesting part of classical mechanics is that if you know the state of a particle at a given time, you can tell about its evolution in the future, you can tell what has happened to it in the past, and that is what states it were in the past, and that is why it is called deterministic mechanics. So, once you know position of a particle and you know its initial condition, you can tell like what will happen to it in the future, how the whole trajectory of the particle will evolve, and whole classical mechanics is based on this, or the classical physics is based on this, and our way of scientific thinking is based on this principle. So, it from t it has moved to a point just a little bit time. So, instead of looking at one instant, you are looking at just what has happened if it just gone a little bit ahead. It is a very intuitively difficult concept, and then he says let me now look at the speed or average speed it has taken. So, because it has gone a very little distance or at a very little time, the time elapsed is so small that the direction possibly has not changed, as a result of which it still remains a vector, but we are computing its magnitude. So, now we are taking the velocity. So, this is what is a change, this is what we will feel that okay, this is the average speed basically. This quantity x t plus delta t minus x t by delta t is average speed. Now, what Newton said that I want to look at it only at a given point. So, at the point t. So, what I do is I keep on decreasing my time interval delta t. So, hence there first came in the concept of limit, where he is talking about what happens to this ratio when this limit what happens to this ratio as I make delta t smaller and smaller and smaller. Remember, if I make delta t smaller and smaller, this distance also becomes smaller and smaller. So, do not think just it is a 0 by 0 thing, I can forget about it. No, the interesting thing is that if this is a number, and then that is called the instantaneous velocity is given in this at the point t. So, this is called the instant, or rather I should write it, just give the same arrow. This is called the instantaneous velocity at the point t, at the time t, and this is a very fundamental thing. It will be very difficult to grasp this feature at the beginning, but then like many things in mathematics and many things in the physical sciences, you start getting used to it, because it turns out to be a very useful idea in describing motion of particles. So, this is also written as Vt, and this Vt is also written as dx dt, evaluated at time t, if you want to say like this. Now, another use of higher derivatives is in the expression of the famous second law of Newton, which says force is mass into acceleration. So, acceleration is the change of velocity. So, force is equal to mass into acceleration, that is dv of dt, change in the velocity. So, derivative is the rate of change. In fact, when Lord Kelvin, J. Thomson was teaching derivatives or calculus to his students of physics in Cambridge, so they got very confused with the very standard way of talking about derivatives. Then he told them, don't worry, derivative is nothing but the velocity. So whenever you are looking at the rate of change of a quantity with respect to time, you are talking about derivative with respect to time. So acceleration is how the velocity changes with respect to time. If you press the brake accelerator of a car, you will see that the car speeds up, so the velocity changes. So if you release the acceleration, it release the accelerator, the velocity comes down. For example, when you are pressing the accelerator of a car moves forward, its velocity increases, or you leave the accelerator, its velocity decreases. Either way, the velocity is changing, and this any change with respect to time is captured by the derivative. And what is the meaning of this acceleration? It means what is the change in velocity if the time changes by 1 unit. That is exactly what is the meaning of rate of change, which is very clear, very natural to understand. But this whole idea came with this bringing of this idea of the meaning of velocity at a point. It is so surprisingly a complicated idea. It is not such a simple idea. I would like you to have a look in the internet on this whole issue. It is not so simple, but it guides all our physical sciences. Now, because V is again x dot t, you can write this as m times ddt of dx dt. So basically this is the second derivative. So the force is mass into the second derivative of the distance with respect to time. So sometimes it is also written as m of x dot dot t. Note, I just want to note just for curiosity that you can write this whole thing as ddt of, because if there is a constant, if you multiply a function c by a constant f and then you take its derivative with respect to t or x, whatever you want, say it is t here. So then the constant actually comes out, it becomes, so here you can pull in this mass, the constant. By the way, mass is also not a trivial concept. So this mv is called the momentum. Force is actually proportional to the rate of change of momentum, and that was exactly what was written by Newton in his Principia. It was not told that force is mass into acceleration. So this is just for your curiosity, and with this I would like to end the talk, and tomorrow we are going to talk about a very important thing without which nothing happens in the world as per Euler. Everything in this universe takes place, never takes place, nothing in this universe ever takes place without some quantity being maximized or minimized. That was that was the thinking of Leonhard Euler, one of the greatest mathematicians of all times, and we will talk about maximization and minimization of functions, trying to find the maximum value of function and minimum value of function, and a thing which I had been in love for the last more than 20 years. Thank you.